Alright, should be another draft physics video presentation. Should be. Having some more problems with the operating system. But anyway, we'll see how it goes. Linux. Anyway, it's better than Windows, right? I mean, anything's better than Microsoft and Google. Anyway, just play the video, Gary. Alright, so more light experiments, shenanigans. So these are Action Lab videos. And he does it's a lot of videos. They're really, interesting, lots of different experiments. But it's the same shenanigans, the same, they have this bad theory and they're trying to force the evidence to match the theory. And it doesn't. And you can show the obvious flaws in, the interpretation of what they're seeing. And you can see that, in some of the, in another video I'd like to get to, hopefully, you can just see the obvious, they say they're doing something and then they're not really doing that,
Okay, today I'm going to be doing an experiment that proves that light is a wave. And then I'm going to do an experiment that shows you that light is a particle. And then after you're thoroughly confused, I'll explain what light really is. Okay, so first I'm going to be proving to you that light acts as a wave. And to do that, I'm just going to be...
Won't even come close to doing any of that. I guess I'll turn the speed down a little bit. That's a little too much. So I did try to use this MPV thing the guy suggested, and then you don't have to see the ads, but yeah, it's a disaster. It really breaks the computer, so can't use that.
Using a standard laser pointer. So this isn't anything fancy, it costs like $5 or something. So the experiment I'm going to be doing is called the double slit experiment. And what it does is it uses the interference of light waves to show light and dark patches of the original source. So when any wave strikes a barrier that has two tiny...
So again, when any wave, and what is a wave? A wave is a frequency, fundamentally, that's what it's built out of. So he's almost trying to say when any frequency, and this isn't true, there's lots of different ways that frequency travels, and it's this stupid wave crap is kind of silly. They know it doesn't happen in a fiber optic cable. The light isn't going everywhere. It's going to specific locations. It's just such a mushy way to describe things.
Little slits that are close together, you can see an interference pattern on the backdrop here.
Right, you can see a pattern. Now the open question is what causes the pattern? Right, but it's not interference.
So basically, if waves come in, so this represents the peaks of the waves.
Right, and as presuming that somehow a photon is spread over this big giant area, when we know pretty much what a photon shape is. Okay, it's kind of a fact. It's sort of shaped like this. It's sort of a little thin thing traveling in this kind of way towards you. It has a definite dimension this way, polarization, and a definitely small dimension, the opposite dimension, and then it has a dimension of length. That's where the frequency is. See, the frequency takes time. You can't make a frequency that just happens, bam, there's the frequency. See, a frequency is a timed event. It has a period. The period is the word they use to describe the amount of time it takes to get from one part of the frequency to the other part of the frequency to the next part of the frequency. So a photon doesn't arrive and say, I'm 500 nanometers. It doesn't just knock on the door and say, hey, 500 nanometers. It takes time for it to say, I'm 500 nanometers. Because it has to basically punch you in the face, and then 500 nanometers worth of time at the speed of light, it punches you in the face a second time, and then it's 500 nanometers. That's the real physics. This fake, phony bullshit is just that, fake, phony bullshit. And he's going to show it right here where he just doesn't care about the facts at all.
And it hits this wall here. What happens is these small little slits here act as point sources for the wave.
Right, so he drew them right in the middle of the slit. That's not the math. That math won't get you the right answer. It's not the point sources. It's not the center of the wave. So that won't work. You could draw these two little waves all day long and you're never going to get the right answer. You're never going to get the vectors that'll be in the right places. You won't create the right pattern. It's just a pile of crap. It doesn't happen that way.
So it starts the wave over again. And so the peaks and valleys of these new...
So just drew the old Young drawing, which is inaccurate and incorrect and doesn't account for the real pattern. It actually has 4 point sources it has to be created out of, and the single slit obviously has 2 point sources, because that's what the variable in the math is the actual distance between the two surfaces, indicating what? Yes, the distance between the 2 point sources that you're going to draw vectors from. So obviously in the single slit, the center of the waves has to be the surfaces. And in the double slit, the center of the waves, the 4 waves, has to be the surfaces. Clearly it's the 4 surface experiment, and the single slit is the 2 surface experiment. That's the actual physics.
Wave sources interfere with each other, so that when the waves hit a backdrop here, you see areas that have high peaks and low peaks, and it looks like a striped pattern.
Right, well it really doesn't. You see much bigger light spots than dark spots, and there's reasons for all that, and none of them will ever talk about them. If you project it on a flat screen, then the areas of light and dark will get bigger and bigger and bigger as you go further and further onto the infinite plane, which, again, we really can't see it as it actually is. So, I mean, they know this already, right? They're physicists, right? They know that, yeah, if I project a regular movie onto a wide screen, it'll get all distorted. Okay, the characters on the outside will get really, really fat, and they won't look very good. They know this.
But in order for this to work, you need light that is coming in parallel lines like this. So
again, this is kind of silly. It's all about the phase of the frequency. So you need the light to be in phase, and that's all. The little bits have to punch people in the face. Like one guy goes to one house, and one guy goes to another house, and they have to be hitting people in the face at the same time. If they're hitting people in the face at different times, then the police don't get the phone calls, because the phone calls overlap at the wrong time, and you can't hear the call that somebody's punching us in the face. But that's really how, if you want a silly metaphor for it, but that's really how it happens, okay? It takes more than one house to say, hey, somebody's punching me in the face, to actually even make a photon.
From a flashlight won't work because any light coming from a bulb source like this is coming from all directions, so it's curved.
And that wouldn't make any difference, frankly. You can do the experiment, it's just that it's not bright enough. That's the real problem. You can't get the light to go through the slits, and it's not really bright enough to create the pattern. And yes, you have a whole lot of problems with the fact that it's not all coherent. So it's better, that's why they put another slit in. So usually when you do it with a light bulb, you just put another slit before you get to the actual slit. And that way you've already forced some of the light to be rather coherent, straight. Same path length.
But there is a source of light you can use that's not curved, and that's laser light. And so laser light is mostly coherent light. And so the peaks and the valleys are all lined up, so essentially it's coming...
So again, it's just about there being little bits of energy, and there's a whole bunch of bullets coming across. And the fact is, though, is you can only receive a certain polarization of the light. And so again, they're just ignoring the subject of polarization, which it's a fundamental feature of light, and yet nobody wants to talk about it. Except when they want to talk about it. Except that when they want to turn it into a metaphor for a spin. Or some other wacky thing. But otherwise, they'll never talk about it, because it makes their theory not make any sense at all again. This is a photon. Okay, I mean, I can just draw little spots on it, but I mean, I shouldn't even have to do it. You should be able to get the idea. Okay, the photon is just bits of energy at a distance from each other, and they're in a distance from each other. Well, that's just totally useless. There, I guess if I get that close, you can see it. See, there's little bits here, one at the end here, and one at the end here. So they're separating in both dimensions. They're separating this way, and they're separating this way in space. Okay, and one's proportional to the other, and that's what arrives at a surface. And this width is 1,000 atoms for visible light. So this length is 1,000 atoms. that means this length is likely that too. Okay, so the idea is that 500 nanometers, the distance between the bangs, the punches, the whatever you want to call it, the waves, is actually, 1,000 atoms, roughly speaking. It's 1,000 atoms worth of distance between these things, so that you could fit 1,000 atoms between this bit and this bit in both dimensions. And that's what the photon really is. And their theory is this big giant thing, okay, with these huge dimensions. There's a little tiny electron here that's 1,000,000 times smaller than this thing. And this little tiny electron receives this entire photon some magical way. How? And it can produce another whole photon back. So somehow this thing 1,000,000 times smaller somehow wiggles so far in space that it somehow can produce energy coming out at this huge dimension. That's what they want you to believe. It's theoretical nonsense.
In parallel lines like we saw in my drawing there.
So again, as I pointed out, if I send a whole bunch of these things, right, the idea is that I send a whole bunch, but they're all kind of, all the little all the places where the dots are lining up. So all of these pieces of paper are all lining up proportional, with the right distances between them. So if you have more than one piece of paper, the other piece of paper is just exactly one node, one node of frequency below the other one, and the rest of it, so all of it's lined up. It all came from a source that was aggravated at the same time. So all of the little slits of paper are all kind of in the same, block of space.
Basically, if I can just pass this laser light through some tiny little slits, then we should be able to see an interference pattern if these light rays are really waves. So it's actually quite easy to do the
Really waves, this proves it. No, it doesn't.
double slit experiment with a handheld laser like this. All you do is put a very thin wire across the opening of the laser, and then you place tape on either side of it.
Which is totally irrelevant. So as soon as he put the wire there, he already decided what the pattern was going to be. And the rest of it's not going to make any difference. Basically, just because the wire's so small.
So that basically when you're finished, you have a wire in the middle with two tiny gaps on either side of it. And so now if I shine my laser light and I see interference patterns, that's proof right there that
all he's doing is, by putting the tape on, he's reducing some of the light, that would just blur out everything. So he's just reducing the amount of light the laser's producing that's not connected to the little piece of wire. But he's really not technically doing a double slit experiment.
light is actually wave-like and has wave-like properties. So let's see if I can see an
So again, wave-like properties, wave-like. Again, it's all frequencies that any concept of frequency has this notion of phase in it. Okay, the idea that the the stuff has to line up. And if if this is the frequency, and then I send the next bit with a frequency here, right? So if one guy is punching somebody in the face, and then only a half second goes by and the other guy punches, but it was supposed to be a full second, you understand they're out of sequence now, and now they can't collectively add up. But that's all it means. It just means that you can't recreate the original frequency. So phase is the only thing this is about. Phase is incredibly relevant to any frequency. It doesn't have to be a wave. A frequency of bullets, tipping something over, it's very important that you hit things at a certain sequence. A pendulum swinging, I'm going to poke it with my finger. I have to poke it at a specific frequency, the frequency of the pendulum, or I'll end up doing constructive damage to the swing of the pendulum. If I want to add energy, I have to hit it in a sequence that is consistent with its sequence.
interference pattern with my laser now. Okay, the double slit experiment. Let's turn on the laser and see if we see any interference. Whoa, it worked. Look at that.
Yeah, obviously can't see much there.
You can totally see the pattern there.
So we'll zoom
That's
in.
so cool. You can easily see the bands of interference.
Right, so they're just bands. That's what they are, okay? And they're not doing what interference would require. If light was a sine wave and all of that crap, it should be gradually go on and gradually go off, and it doesn't do any of that. Okay, they're obviously it's either all on or all off kind of a pattern. I mean, not all. Obviously, it's not as dark as it should be here. You know, the darks aren't completely dark. But anyway, close enough. The fact is that you see a pattern. Now, what the pattern's being caused by is the scientific question to be answered. And my clear argument is they haven't really cared to answer the question correctly. They've just jumped to the assumption that anytime you see a pattern, it must, the simplest pattern in the universe, on, off, on, off, on, off, it must be wave interference. No. There's lots of other possibilities.
Here. Wow. Just by sticking a wire in front of the laser.
So sticking a wire in front of the laser means he doesn't have the double pattern. He's not got there's no envelope pattern here, because he's really taken the two sources. The tape is sort of out of the experiment. He could have just stuck the wire there and got exactly the same pattern, pretty much. It would have been blurred out a little bit because the bright spot would be much brighter, but you'd still see it. So all he's really getting here is the wire pattern. So he did his single slit experiment in the sense he did the two surface experiment. He didn't really do the four surface experiment.
Okay, so I just proved to you that light is actually...
So, this is all part of the game. Let's say I prove something. You didn't prove anything. You didn't prove what went in, you didn't prove what went out, and you didn't prove how it went out and what it did to come out that way.
Made of waves, or has wave-like properties.
Oh, wave-like properties. Again, this mushy rhetoric, whatever that means. You're describing a reality, okay? To say it's horse-like. I mean, I could look at some people's face and say they have horse-like properties. Big nose or something. Is that being, a good scientist?
But now I'm going to show you that light is actually made of particles and has particle-like properties. And in order to do that, I'm going to use some glow-in-the-dark material. This specific one is called Lit. It's actually a really cool glow-in-the-dark pigment. So how glow-in-the-dark materials work is they have some...
So this is the good part, because now we get some more theory. Now it's good that he does videos and he explains theory, but the theory is just wrong. I mean, it's not based on anything except, well, this is the theory. We've jumped to this conclusion. But we're not really going to explain anything like polarization and all the other stuff that you have to explain. So we're not going to really explain what light is, the physical properties that light really has. We're not going to be able to associate that with what we're going to describe.
Electrons. This is my electron here, and they're at their base state here. But when a specific kind of light hits it, it knocks it up to a higher energy level. And
so you could understand that, right? That electrons in matter are in stuck positions. So this is where I'll have to show you what the alternative explanations could look like that are so different and fit so much better. Yeah, just so much better. I have to, hopefully the other camera works. I guess I could pause. Well, maybe it's a good thing to do. Alright, I think that's close enough. I hope this video is going to save right. I just don't know how broken the system is actually been broken by that stupid piece of crap. Anyway, just complaining. It's just irritating. You never know how much it's broken, and then you don't know whether the last copy you saved of something is the broken copy or it's still working. Anyway, all right. So the idea is that we've all heard this part anyway. That the atoms basically have these energy levels. They call them. They're just places. Where even if you think of it as a magnetic model, if you think of the electrons as being in positions. And you think of the fact that if I was going to add another electron, and they're being held in position by the repulsion, I guess we'll draw that as red, the repulsion to each other, I don't know how much that shows up. Really not at all. Oh, okay. Great. Alright, I guess we got to zoom in a little bit. That would be an answer maybe. Alright, I'll pause. Alright, that might work. I just have to remember I don't have much space to work with. Alright, so if you have this repulsion, we'll just draw as red, between all of these electrons. So you can understand they would find positions where they were balanced, in terms of balancing against each other. So they would have a dynamic. And then there would be the attraction, so to speak, the low pressure. So they have high pressure towards each other, so they balance to that, and they have low pressure towards the nucleus where the protons are. So they're all going with this low pressure to the proton and the high pressure to each other. And you can understand that they would be in a tension then. And the ones on the inside here would be in a lot more attention than the ones on the outside here. A lot more distance between them, a lot more or less pressure. And as you go out, they have kind of the inverse model. They think the inside is weak and the outside is where the strong forces are, which I would say is exactly opposite. But anyway, we both agree that there's these zones that are habitable. So I would say it's the same thing happens with a magnet. If you have a magnet and you have your field lines around the magnet, the silly, arbitrary lines they are, you're really saying that these magnets end up lining up the same way, north, south, in the same way. So they're repulsive magnets. So something just can't exist here in the middle. It just can't live there. It has to decide, I'm either going to this side or I'm going to this side, and it's going to do it very fast. And that's the same idea here. If an electron gets jolted out of this position and pops to this other position, it's going to do it fast. Once the decision is made that you're not going to be able to stay here, your trip over here is fast. And I've sort of argued this whole thing is just about how fast you're moving electrons and how much you move them. So the idea would be in actual space, if I hit an electron with energy, all it does, an extra bit. So the universe is doing this, and this on both sides, and the electron's perfectly happy. But I add one more bit going this way. The idea is the electron's now not going to be happy, and it's going to be forced to change its position, and it'll go to some position here before the drag, the opposite force that it went into, stops its motion. And so it'll change its position. And that's all you're going to get out of it, though. You're going to take this, and you're just going to move something this way. Now, the trick is when you hit a piece of matter, an atom, it has this spring built into it. Okay, this whole thing is in tension. And if I wobble it a bit with one piece of energy, it's going to fight back, just like the Earth fights back to gravity. So gravity is just a force going this way. The Earth looks like it's just saying, I'm perfectly happy, okay? It's not doing anything. And it only does something when you push into it, right? So when you push into the Earth, that's when the Earth fights back. And you have these two actions. You have the Earth moving down, so you have this preserved. And you have this new reaction, this new piece of energy going this way. And that's going to affect the universe back this way. So this piece of energy is really going to have two components. It's going to have the component that's going to keep going this way, and it's going to have this component reflecting, coming back. So one action causes two actions, and it's because there's a bunch of tension built into the atoms. The atoms are what's pushing back. The pressure you're putting on the atoms, you're squishing the atoms, and the atoms aren't accepting the squish because it has a shape it wants to stay. Its geometry is saying you can't do that. I'm going to go back to what I was. And the going back to what it was is going to look like another piece of energy. So so you have to sort of understand that when a photon, when you hit a piece of matter, a piece of complex matter, and you do this thing where you're going to change where the electron is, you're really taking an object like my hand, and you're either pushing it this way. Now when I pushed it this way, what did I do to the universe on the other side of my hand? I basically made my hand disappear, right? So I give you a bunch of reflections, and I give the opposite direction no reflections. And then when the hand bounces back, it does exactly the opposite. It creates a bunch of pressure going back this way, a bunch of reflections, and you don't get any reflections. So that's the on and the off, and the on and the off. So that's what happens every time an electron moves, okay, theoretically. What it's doing is it's moving into a force. It's like you can just think of it as a swatter on a stick. It swats this way, and if you don't hit it with enough energy, it just moves right back again. Okay, and then so it swats in the opposite direction. So it creates a little bit of energy popping off of it, reflections, a little extra, a little more. But when it jumps from a complete jump, that means it's traveling a much longer distance. So it's pushing a lot more stuff, and then it's creating a vacuum of stuff when it goes back the other way. And that's the real trick, is the speed at which the electron moves means it will create a lot more reflections or a lot less reflections. And those little reflections end up being what we call a photon. So again, this really is just as simple as, if I want to send you a signal, all I have to do is this in space, right? And theoretically, I've sent you a signal. It really will be a change in the energy hitting you. So I can just stand way across the room. I could stand on the moon, and theoretically, some of my signal might actually be getting to you. But it's going to be so weak that you're not going to be able to detect it, right? But you can theoretically understand that there's no denying that the sun bounces off my hand pushes more photons when it's moving forward because it bangs into more. It reflects more. And so there's a lot of reflections. And if I move my hand really fast backwards, there's very few reflections. And if I move forward really fast, you can get the idea that I can send you a signal with that crude a device. And yeah, I'm not waving a substance, I'm waving, okay, the fact that there's photons in the air and there's all kinds of energy hitting me all the time. And when that energy will get to some other location in the form of a reflection is completely dependent on my position. So if I change my position, I change when you see a signal. It should be enough. I want to close that and start this.
It stays there for a while. Normal materials, as soon as they get knocked up to a higher energy level, they just fall back down and they re-emit the light in a matter of nanoseconds.
Right, so that's another key to this whole thing, is understanding what's the difference between light that's purely reflected, like glare, right? Glare is like real reflection. It's like the light that the sun sent didn't get fiddled with very much. But the trick is the only light that can do that is light that is polarized in one direction. So the sunlight that's coming in the different directions, it's not going to get through. So only light that's going nice and vertical with the reflected surface is the light that's going to turn into glare. And then all the other light is really absorbed light, and then it's re-emitted. The photon you push in isn't the photon you get back out, in a sense. You're pushing the system, and the system pushes back. It's not a pure reflection. And I would argue the difference is the difference between hitting electrons and hitting protons. When the energy hits protons, it can quickly reflect because it's just being converted into a 90-degree turn. When it hits something close to that. When it hits other stuff, when it hits the electrons, it moves them. And by moving their position, it's giving you a new picture of the world. And that's really all it's doing. It's just changing the position of the electron. And by changing its position, you're changing your view of the universe. It really is the truth.
For glow-in-the-dark materials, they get knocked to a higher energy state and they stay there. And the reason they stay there is because in order to fall back down, they have to go a different way. They have to go through a different transition state.
Right, so he doesn't really explain any of that, why they have to, but it's because of the complexity of the geometry of whatever the molecules are. So if the molecule is a little bit complicated, you can understand that the path back, to get back to your to pull an electron back after it's been moved out will depend on it. Everything has to line up, right? I mean, they have to all be in the right position for they're for the imbalance you've created in the internal system. The internal geometry is now a little imbalanced. They only got 3 things in it instead of 4. So it's created a different shape, right? It was a square and now it's a triangle. And now you're going to try it tends to want to get back to that consistent shape because then everything lines up. But it takes a while for the wobbles and the processions of all the different orbitals to get into the right alignment to actually push the thing back in. So for some substances, it takes more time because they're complicated enough where they have to twist and turn a few, it's like a Rubik's Cube. They have to turn a few times before everything lines up, and now it can get back to where it was. So it has to do some alignment before it can do its, I want to get back to my original condition. So it has to go through some cycles before the geometry is right to get it rebalanced. It wants to rebalance. It's jiggling because it's imbalanced. It just has to jiggle the right way to be able to line everything up so the electron can pop back to where it belongs.
Called a forbidden transition. And the forbidden transition means that it's very statistically unlikely to happen. So it takes a while for it to...
So it's not that it's statistically unlikely to happen. It's that it takes time for the energy, the disruption you've created in the atom. You've disrupted the atom. It takes time for the disruption to wobble through everything, cycle, and then wobble back down again. So it just takes time for the change in the pressure inside the atom you've created to be able to organize enough to go the opposite direction and put the energy back where it belongs. You've created a kind of scatter and it has to normalize before it can fit where it belongs.
Happen. But eventually the electrons will fall back down, and when they do, they emit some light. But here's the weird...
So again, it's not falling back down and all these other kind of jargon. Okay, the light's going to be emitted because something else is going to move. Or you're actually moving the electron back to its position, which is, sending the off signal. But, because it's going to move away from you. Where before, the energy you put in was away, and then in the sense you're pushing something away, and then it's going to be pushed back to a position. The push back is the photon you see. It's just a different phase of the same energy.
Thing about glow-in-the-dark materials is that in order to knock this electron to a higher energy level, all types of light don't do it, but it takes a specific color of light to do it.
Right, and color just means frequency, so that's all you should say. It takes a specific frequency. And why would frequency be important? It would be important from a very simple reason. See, now they have this complex view of the atom as this thing with all this stuff orbiting, and it really gets hard to understand how frequency could make any difference. But if you understand the electron to be in a position, and you understand it to be sort of locked in that position, that is, attracted to a proton, like a magnet. I can create this with magnets, right? You can understand. I could take 2 north face magnets and 1 south face magnet, and I could suspend another magnet here, and he's not really going to go anywhere. But to make him go somewhere, if I hit him once, he won't go anywhere, because he'll just bounce back to his comfortable position. But if I hit him again before he can bounce back, you can understand, well, now I can knock him out of that system. I can knock him out of that comfort, that balance. So all you're doing is saying what frequency of light does it take to unbalance the position of the electron. So at a high enough frequency, I hit it while it's still moving away. And if I hit it while it's still moving away, I'll add energy to its system. If I hit it when the pendulum's swinging back, I'm not going to win anything. I'm not going to move the pendulum. If I want to move the pendulum, I have to add the energy, okay, before the pendulum swings back.
So for example, if I shine red light on this glow-in-the-dark material, no matter how strong of light I shine on it, the electron won't get knocked up to the higher energy level. Nothing. No.
So again, it doesn't have anything to do with the energy of the red light. The red light has plenty of energy. There's plenty of people walking up to houses and punching people in the face. It's just that they're not doing it in the right sequence, to be able to cause the cascade, to cause the reaction. So they're not hitting, say if the people in the houses were pendulums, by coming in and hitting at the wrong timing, they're hitting too many people when they're coming towards them, kind of thing. Well, that would be more effective actually in breaking people's faces, but it's for this analogy. Yeah, I ought to get a better analogy.
Charge whatsoever. But if I shine just a very dim blue light on it, the electrons will get knocked up to the higher energy level, and you can tell they did because they eventually glow and re-emit the light.
Right, so you've basically taken electrons from high pressure and you've moved them, from low pressure, and you've pushed them into the middle. So it's the opposite of what they would argue. You've taken electrons that were on the outside, weakly held, and you've pushed them into the high pressure zone. So now instead of 4 things, there's 5 things in the middle. And the 5 is now dicey because it's screwing up these other outside shells because they were all organized based on this box figure. And now a square, and now you're throwing a fiftagon at them, pentagon or whatever it's called. Now that's going to screw up the balance. And so, eventually there's going to be a point where the jiggling and the wobbling of that atom will push that pentagon back into a square.
So what's weird about this experiment is that it disproves that light is a wave. Because if light were a wave, all you would need is very high amplitudes of a specific light.
So this logic doesn't make any sense, right? Because we already know this amplitude thing would be a real problem in terms of the space it takes up. You have to account for the space you're consuming with your photon. So how can you increase the amplitude of the wave? Isn't it spatial? So it doesn't make any sense. And really what the argument is the amplitude would be the volume. So that would just be me saying how many bullets you fired is one thing you can do. And then how fast you fire them is another thing you can do. And I would argue that you're going to tip different things over. You'll add energy to different pendulums. Different weighted pendulums will have energy added to them depending just on the frequency. And it really doesn't matter. I can shoot bullets. I can shoot 1,000,000 bullets at the pendulum. But if I shoot them at the wrong frequency, the pendulum doesn't get any more energy. If I shoot them at the right frequency, it adds energy. It's that simple, really. The faster I shoot them, the more likely it is I'm going to be on one of the resonant frequencies. You sort of defeat this whole problem of resonancy, being on cycle, the faster you do something.
And eventually you'd be able to knock electrons up to the higher energy level. But what I'm telling you, that even if you had enormous amplitude, extremely high intensity of red light, you still couldn't knock this electron up to a higher energy.
Right, and the idea is you've got to knock more than one. So the whole point is the photon is this big object, and it's going to take more than one electron doing the same thing for you to create something called a photon. One electron doing this isn't going to make a photon. Because we know we can't make a photon that isn't have large polarization. That is, the signal covers a lot of space. So the electron can't be jumping to all these different locations, that are 1,000 atoms difference. It can't jump from one house to another house and make this photon. It's clearly numerous electrons have to have the same thing happen to them, and then you'll get a photon.
Energy state. But even with a very, very, very dim blue light, you would be able to knock it up to the higher energy state. So an experiment similar to this one called the photoelectric effect is what led scientists to...
So which is very deceptive because there's 2 effects. There's kicking an electron out of an atom all the way out. And then there's this idea of just moving it around inside the atom. So moving it around inside the atom changes the shape of the atom, polarizes it, creates magnetism. So that's electricity. Just changing the shape of atoms creates what could be called a cascade of electricity because all the atoms are connected to each other. They're sharing electrons. So if one atom expands or contracts, it means all the other atoms are going to end up feeling that expansion and contraction, and they're going to be reacting to it, and they're going to be doing the same thing in a cascade. And that cascade of change in positions again, as I change the shape of the atom, it means I change the positions of the electrons, which means I change what they're reflecting to the world. So if I change their shape quickly enough, again, we're just back to this simple argument. If I move my hand fast enough, you can understand that if it's moving away from you, you won't see it at all, because it can't reflect any light while it's moving away if it's going fast enough. And if it's moving towards you, it's going to interfere with all the photons in that path, and it's going to reflect all of them at one time. All of them are going to go back to you at the same time, even though they were in different places in space. If I move my hand theoretically close to the speed of light, all the light in all of these places, all the light in all of the positions in space, all those positions, they all end up reflecting to you as if they were in one position. So I've increased the amplitude of the light tremendously, because I've taken all the light that would have fallen in all of that amount of time, and I've sent it to you in one piece of time.
Developed the field of quantum mechanics. And what they said is that light actually isn't a continuous wave like this, but it's actually made of discrete particles. And those discrete particles have specific momentums.
So that's the funny part, right? I mean, the discrete particles can't have specific momentums, right? So even if you were to say, even if you were to buy this, even if you could draw this in some way, what he just said, right? He just said that they're conceding that light is made out of particles, when that's not what they're conceding. And clearly, the particles wouldn't have the frequency. The particles would be making the frequency. They're the components that make the photon. They're not the photon. They can't say, I'm a 500 nanometer particle, or I'm a 250 nanometer particle. They can't do that. They don't change their momentum. They're the things with the solid, consistent speed of light thing. And they're all quantized, which means they all have the same mass. So again, they have a Planck mass and a Planck velocity, and all you're really saying is the only thing you can change about them is their frequency.
And in order to knock an electron up to a higher energy state, it has to be hit with a particle that has enough momentum to knock it up to that.
Right, so they think it's one little bit, it's hitting it and then knocking it to another state, when clearly you can understand it. No, it's a tipping point argument. You have to hit it more than once. That's the whole point of the frequency. I mean, it's just so unintuitive to talk about the particle and then just ignore frequency. To talk about light and ignore frequency would be retarded. It's clearly a tipping point argument. It's clearly this simple argument that you have to hit it when it's not moving back. So if you can hit it before it moves back, you can hit it a further distance. So it's just about the rebound speed of the electron. If you can hit it faster than its rebound speed, you're going to move it a lot farther.
Higher energy level. And that makes sense, right?
No, it doesn't make any sense at all. Sorry, no. Not even close to making any sense. One thing hits and it just pow. And somehow it's a double power because it's a faster frequency. Why does the bit have twice as much energy? Because the frequency is faster. No, the bit can't have more energy. The more energy is in the fact that this is a system you're hitting. It's a pendulum. It has rules. And its rules are telling you you have to hit it at the right frequency to make something happen.
Not just any particle can hit it, but it has to have one that has enough momentum to knock it up there.
So again, just more silly talk. So again, the red light has plenty of momentum. It's just the momentum is poking the pendulum in the wrong sequence. It can't make anything happen because the pendulum always swings back. It hits, the pendulum always swings back before it hits again.
And so it turns out that red light doesn't have enough momentum to knock electrons up to the higher energy level, but
doesn't have enough frequency. The frequency isn't fast enough to overcome the rebound speed of the electron. That's the physical facts. That's what makes sense. Those are the right and accurate way to describe the reality. Theirs is just mushy, silly talk.
Blue light does. And so just this simple experiment of trying to charge a glow-in-the-dark material with red light versus blue light shows you that light is actually not made of waves, but it's made of particles. But
it really doesn't, okay? As much as I'm saying, yes, of course it's made out of particles. Because, again, you've misdescribed the photon as you're turning this obviously an event that happens over a sequence of time. That's what frequency is. Frequency is always something that happens over more than one click of time. it can't just be spontaneous frequency. Or instantaneous, sorry. You can't have instantaneous frequency. The whole point is the frequency means they're events taking place in time.
Previous example, I just showed you the light is
Over time. And time means distance. That's the wavelength. The distance between the initiation of an action. A photon is a sequence of actions initiated.
made of waves. So now for my final really weird experiment. What if I shine the double slit experiment red laser light on this glow-in-the-dark pigment? Will it charge it? Okay, now for the experiment that puts the cherry on top. I'm going to be shining my double slit experiment laser light onto the lid.
Double slit experiment laser light. I mean, it doesn't even make any sense. He's just going to shine a red laser on it, I guess.
And showing you that it can't charge the lit. And if it's not registering how crazy this is.
Let's see. If light were waves, it should charge it. If light was particles, it shouldn't. So this is just, you know, you're going back to nonsense. But clearly, if the light is only at the limited, if it's all red light and it's all the wrong frequency, then it has no hope. But the truth is that if you put the light out of phase, then you can create new phases of light that could.
I'm going to be showing you that I'm shining waves on it because you can see the wave interference of the light, but then the intensity
I didn't watch this part, so this ought to be interesting.
is 24 times greater than sunlight, but it still can't charge the lit because the particles of red light don't have enough energy to knock the lit up to the higher energy state.
What would be interesting is if he really did this all mathematically precisely. That is, you know, set up a real experiment to do exactly the same location, and then see if in the lit, whether the bars are in the same place. Because maybe it's the dark spots that are glowing now.
Okay, so here we go. You can clearly see the slits on there that show you the wave interference of light.
So again, he should do it with a little bit bigger pattern, done a little more professionally. But you know, I would argue that the dark patches are actually where, right in the middle of the darkest line, means that you have two red photons, right? Or the red photons are hitting completely out of phase, which means, you know, that 180 degrees out of phase thing, right? I mean, I hate to do the blackboard. I mean, they're here and the other photon is here. The on-offs are exactly the opposite. So when this photon's on, this one's off, you know, and vice versa. And what that really means is you've created a frequency that's actually, you know, 250 nanometers. So the 500 light, you know, the 500 frequency of this is turned into half that, because if you combine the two, you have a consistent frequency between them at 250 nanometers. But it only happens in that one spot where you actually get them lined up, you know, exactly out of phase, 100% out of phase, you could argue. And that might charge the material, ironically, right?
But it looks like it's not charging the lit.
See, it's just not a good enough experiment.
But if I just shine an ordinary flashlight that's orders of magnitude lower in intensity onto the lit, it easily charges it.
Well, it's clearly white light, so it has the ultraviolet in it. So, yeah. Duh.
Crazy.
You can still see a little line here, so I just don't, you know, he did lower the light. So he never lowered the light when he did that, right? And that's kind of a defect right there. But
Okay, so what I just showed you is extremely weird. Basically, I showed you that when the light was coming out of the laser, it was a wave. But then when it hit the glow-in-the-dark material, it turned into a particle that didn't have enough momentum to knock the electrons to a higher energy state. So it was a wave with...
So again, when he says momentum, again, if you just understand that if the electrons are in tension and they move back, so if you don't hit them hard enough, they just move back to their position, and now you have to hit them all over again. So again, I've said this tipping point thing over the last 3 years, 64,000 times. I won't get any counter argument that that's the more rational way to describe the phenomenon. It's just about the fact that you have to kick the electron out of its position, and you have to do it by adding energy to its system rather than subtracting energy. You have to hit the electron when it's moving in the right direction, or at least it is already in a new position further away. If you wait for it to get back to its original position, you won't move it any extra distance, no matter how many times you hit it. The only way you can move it extra distance is to hit it before it can go back to its home.
It left a laser, and then it turned into a particle right about here. So what is it? Is light a wave or a particle? It can't be both, right? I mean, a wave has no specific location. It's spread.
Particles explain waves. Waves don't explain particles. So clearly that's a one-way street that's easy for anybody to understand. I can draw you a picture of how soldiers can look like a wave. You can't really draw me a picture of how a wave looks like a soldier.
Out in space. You can't really say a wave is here or there. It's kind of everywhere. But a particle has a specific location. You can say a particle is right here or right there. But you can't say something is both a wave and a particle.
And you really can't say something with a frequency is one object. It can't have a frequency if it's one object.
So for example, in this double slit experiment, if I say that light is a particle, then does that mean that that specific particle splits into two, goes down both sides of the slit here, and then recombines later? What we say is that light...
No, of course it doesn't. Of course it just scatters. All the photons scatter. Their frequency, their phase gets misaligned, and on the target you recombine the phase in some locations and you don't recombine phase in the others. So all there is constructive reconstruction. The slit experiments scatters light. By scattering it, you're breaking some of it. Okay, it can't be seen unless you put it back in phase. And the only place you put it back in phase has certain mathematical, geometric requirements. And that's as simple as it is.
It has a wave-particle duality, meaning it kind of takes on properties of both. But what's weirder than that is not...
Yeah, no, that's just pathetic. It's not weird. It's a pathetic explanation.
Only light that takes on a wave-particle duality, but in fact all known particles in the universe have a wave-particle duality.
So again, that's just so made up and so silly and so nonsensical and just absolute rubbish. And there's absolutely no... He won't ever do an experiment proving that he has a wave and particle duality, or a Volkswagen or a Cannonball or any of those things have any duality issues.
Duality. So if I were to do this double slit experiment, but instead of using light, I was shooting electrons through, you would actually still get an interference.
So again, this is fake, okay? So I'm just telling you, this is all fake. This is not a double slit experiment with electrons. It's not. This is a scatter experiment off of a surface. This is not what they claim it to be, okay? It's not a double slit experiment. They're just lying. It's a different kind of experiment, and it's different in, completely different. It's not a little bit different. It's completely different.
Interference pattern. I mean, these are electrons, right? You're talking about single electrons, and you can even shoot them out one at a time.
Again, says them, but even if you could, yes, shoot them out a single time, they're not putting them through a double slit. It's not the same experiment. It's a completely different experiment. They don't even know what energy they're actually receiving on these screens. This is talking about a fluorescent screen that'll light up if you hit it with ultraviolet light too. It'll light up if I hit it with a gamma ray. So it's not just electrons in these experiments. This is really it's just a lie. I mean, yeah, what do you want to call it? I mean, they're so exaggerating. This is like calling, all cars Lamborghinis and just pretending that, oh yeah, even though you just have a Volkswagen, you're going to call it a Lamborghini. It has Lamborghini-like properties. Oh, bullshit.
And you'll still get an interference pattern on the backstop. So a wave-particle duality basically means that everything in the universe doesn't have a specific location or momentum until you measure it. So
yeah, well, whatever. This is just such a pile of... This is where they put the cigar in the bear's mouth, and he lights up with his Bic lighter that he bought at the drugstore. I mean, this is just such a pile of shit.
Here's what I mean. Let's take a hydrogen atom. So in the center is the nucleus, but we want to know where the electron is. So let's say we measure the electron and we find it here. But then next time we measure it, we find it here.
Right, the next time we measure an atom. Well, we can't do any of this. None of these measurements take place. None of these experiments can even take place. You cannot know anything much about an electron because it's so damn small, and it's making photons. You can't be sure of what it's making, and how it made them. So you can't even interpret the data it's giving you as single elements. You have to have more than one of them to even get a photon out of it. So again, this is just such a lie that we have any experiments where we can watch electrons, individual electrons. All we can do is watch a group of electrons. And so they're saying because a group can be in different positions, the individuals in a group can be in different positions, they're basically saying that all the members of the group are in all the positions all the time. That there's just not a number of chairs and there's one electron per chair. No, every electron is in every chair. It's idiotic, it's silly, it's nonsensical, it's totally unnecessary to believe any of this horse crap. It's, again, just like me trying to convince you that when I roll dice on a dice table, that the dice entangle and superimpose, and that the two dice don't have any position, and they're in all the positions, and they're in all the possible outcomes at all the possible moments, when you know that's not what really happens. The dice are tumbling through real space. They have real momentums. They have real locations.
And the next time we measure it, we find it here. And the next time here, 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 here.
Yeah, it's not the same electron. They're just saying that when I sat there and said, Joe, well, okay, Joe was sitting in seat 22. And I say, Jim, well, Jim's sitting in seat 1. I mean, this is idiotic. And they're just saying they all were sitting in the same seats. And they're all in each other's seats. And it's silly.
And if we do it lots of times...
Yeah, so group behavior is different than individual behavior. But yes, individuals make the group. So I can send soldiers and I can make them look like the letter 5. I can have a marching band at a football game, right? I can have them spell words and the whole word moves across and they can do all kinds of things. Does it mean that they're all superimposed? Does it mean that some wacky bullshit has to be going on? No, it doesn't mean any of that. It just means that, yes, you can have patterns within particles, and that's it. Individuals can have trajectories, and those trajectories can be defined or confined by rules. And for a marching band, you can have kind of complex rules, and for scatter, you can have less complex rules.
Then we can get this probability distribution of where we're likely to find an electron. So what I'm telling you is that before you measure something, you cannot know with certainty what its property will be.
No, it's just silly. So we know that everything in the real universe doesn't function that way, and you're just making up a story for the things we can't see, and you're just including gremlins and witches and warlocks and all kinds of crap because we can't say, we can't take our magnifying glass out and say, those are brine shrimp, okay? They're not sea monkeys. They're not monkeys, you liar. They're little fucking crustaceans swimming around in the water. Why are you telling me this fucking silly story about your fucking sea monkeys and living in their little sea monkey land? You liar. I mean, they're no better than, those kind of old advertised, look up sea monkeys from the 50s. I mean, it was a big thing. It was like in every single magazine you bought, every kid's thing you bought was selling sea monkeys. And it was just such a deception.
You can only know the probability that it will have some specific...
The cool thing is, though, they'd also sell seahorses, and they were real seahorses. That was really cool. You could buy seahorses, yeah. They'd send them to you in the mail, and they were little tiny seahorses, and they had babies and everything. It was really pretty cool. I had them. A little difficult to keep alive very long, but it was damn cool.
Property or have some specific location. And if you've taken any chemistry courses, you actually already know this, but it was told to you in a different way. So for example, you may have seen a hydrogen atom with an s orbital. So when you're saying an orbital of an electron, you're basically just saying...
Maybe I should just see if I can still buy seahorses that cheap. I mean, it would cheap as shit, $2 or something. You get a pair of seahorses.
That here's the location that you're likely to find an electron when you measure it. So that's why in chemistry, when you see s orbitals or p orbitals, it's talked about as a cloud. It's
yeah, so this is just, like I said, all this is all just made up. There's no reason for you to believe it. They've just made up this crazy, wacky, silly story to explain an event. and this is Clue or something. It's Mr. Mustard, and did it in the drawing room. Except their story is so silly. They're saying the blob from deep in the earth, or the fire blob monster did it with whatever, the laser knife, in the whatever 4-dimensional silly room. I mean, they aren't connecting anything. They aren't connecting any dots to anything rational. They're just connecting a bunch of silly ideas and concepts they just completely made up out of nothing.
Actually not a cloud of electrons, because whenever you measure an electron, it's at a single point. But what electron orbitals actually represent is the probability that
it's group behavior. It doesn't represent anything. It just means that we know that the events that take place will be different over time, and the electron will be in a different place in a different time, and that overall places take shapes, and that's all. There's certain allowed places it will be and places it won't be, and that's just the truth. But it's never in all of them at once, and it's never, ever, ever, ever not in any of them. It's always in one of the chairs. So there's one electron, and it can be in any one of the chairs is the real point.
You'll find the electron in that spot when you measure it. And what I've shown here is the basics of quantum mechanics. Quantum mechanics...
Garbage mechanics, rubbish sea monkey mechanics. This is sea monkeys.
Mechanics is actually the most proven theory in all of science.
Oh, God. Whoa. Whoa, you shouldn't be allowed to fire stinkers like that. You just should be shot right on the spot. I don't even understand where you get how can you be so fucking arrogant to say this shit about this piece of crap? There's tons of theories much better proven. Theory of evolution, for example. The theory of up and down. I mean, left and right. I mean, there's a ton of things a fuck lot more proven than your silly gremlin story.
Hey everyone, thanks for watching this episode of the Action Lab. I hope you enjoyed it. I hope you learned something.
Yeah, you learned bullshit. You learned that people are just really arrogant, and they really don't do anything carefully, and they really don't give a fuck about getting to the truth, and they don't care about how fucking silly it all sounds. Like, you don't care how silly your hair looks. But anyway, it's not a very good style for you.
Or if you have any suggestions.
And the half beard thing just doesn't work at all. So, yeah, he fixes that later, I think. This is how old is this one? Oh, it's only 2 years old, so. Looked pretty dorky 2 years ago.
Questions or comments, let me know in the comments section.
Yeah. Sure. I'm sure you're going to pay attention. Yeah. Anyway, there wasn't 600 ads on this video, which is surprising. But some of his videos, it's just ad after ad after ad. They just inundate you with them. So that was interesting. I don't know where the ads went. Alright, seems like this video is long enough, so I think I'll just do another episode the next time. Glaringly bad. Light cancellation. So he's making the I can make light disappear argument. Yeah, and it's so bad. It's such crap physics. I think it's right here, maybe. No, neither one of those are it. He's got a lot of videos, so maybe I'll play 10 of them or something, and because he makes the assertion and tries to connect it to the evidence, and as like I showed here, the connection there wasn't any direct lines here at all. There wasn't any showing you of how a wave can possibly, a gigantically polarized photon wave can do something to one electron, and the one electron can send the wave back. Yeah, no, not even close. Alright, so till the next time and such, we'll just hope we have a video and leave it at that for now.